And so for those of you who don't know me, also, I am Megan Peters. So actually, before we get going, maybe because the folks who are here today may not have come to your talk yesterday, Lisa, do you want to say a few words just by way of introducing yourself, and we can do the same for Pascal before we get going?
Sure, that sounds great.
Okay.
Oh, and I think we've solved the audio problem from yesterday.
Oh, great.
So
Good.
I'm super excited about that. Anyways, I'm Lisa Miracchi. I am an assistant professor of philosophy at the University of Pennsylvania. And I work on the intersection between philosophy, neuroscience, artificial intelligence, robotics. I'm really interested in how either natural or artificial systems might give rise to beings like us with consciousness, with minds that can perform intelligent behaviors. And so I really do a lot of work with scientists to try to figure out how should we be thinking about these empirical problems.
Great. And thanks. And Pascal, would you tell us a little bit about you so we have a background?
Yeah, briefly, I would say it is fair to say that while I'm currently faculty in the Department of Psychology at NYU, I did get my PhD in what could probably best be described as computational neuroscience at the University of Chicago. And, I've been interested in questions like this for probably over 20 years now. My current research is not on that. I mostly high throughput behavior and how to model that and things like that. But yeah, I mean, that's probably fair to say.
Okay, fantastic. Thank you. Okay, and so without any further ado, why don't we get going on the talk? And then we can have a good long Q&A afterwards. So as a reminder, everybody, please use the Ask a Question button at the bottom of your screen to ask questions along the way. Anything that kind of pops into your head that you want to go back to, that Ask a Question button is a great way to do that. And yeah, let's just get going. So please, Lisa, take it away.
Great, thanks. Okay, so today I'm going to talk about how computation relates to thought. So we're going to ask the question, what's the difference between representational content in the brain and the contents of our perceptions and thoughts? Does the difference matter for modeling the mind or the brain? I'll argue that keeping the personal level contents, that is what agents see and think, separate from what neural or computational processes represent, is crucially important for neuroscientific progress. In particular, I think we should not identify Marr's computational level of description with a description of personal level thought. Instead, the information processing necessary and sufficient to build intelligent systems may differ from the correct person-level characterizations of those systems. So as an example, towards the end, I'll discuss some work by me and my robotics collaborators about how Gibsonian affordances might be implemented in robots that don't represent those affordances. And if you don't know what those are, that's okay, we'll get there. All right, so here's one of the slides from one of your intro lectures showing how many different scales neuroscientific models can aim to cover. And if you were in the talk yesterday, there's going to be a little bit of repeat, not very much, but I want to make sure everybody gets on the same page. So if we're interested in how features of our brains give rise to features of our minds, we're not just interested in modeling one of these levels or multiple of these levels, but we're actually interested in the relations between these levels. And most importantly, how lower level neural features give rise to mental or personal level features. So influentially, David Marr proposed 3 different levels of description in neuroscience, which I think by this point you might be aware of, yes?
Yeah, we did it very briefly on the first day, basically. But yeah, please go over it again, because we've got a broad audience here. So
Great. So for Marr, the computational level is a description of the computation that's performed by the system. So for example, computing a 20% tip, that would be a computational level description of what the system is doing. The algorithmic level is the way the computation is performed. So for example, in order to compute a 20% tip, you might multiply the cost of the dinner by 2 and then divide by 10. Another algorithm would be to first divide by 10 and then multiply by 2. Those would be 2 different processes for performing the same overall computation. Then there's the implementational level, which are the actual physical features of the system that carry out the algorithm and so the computation. So one way of framing our question for today is we can ask, what is the relationship between Marr's 3 levels on the left and these levels of scale on the right, between these different kinds of things we might be modeling in neuroscience? Okay, so the standard answer is that the mental level, the sort of highest level of scale that we're interested in neuroscience, is a computational level of description. So, and many of you have probably been taught this without even thinking about it, that the level at which we have perceptual experiences, make decisions, have memories, and so on, is just Marr's computational level of description. These computations are then implemented in the brain, and it's the job of computational neuroscience to understand what mental computations are being performed, by what algorithms, and how the brain implements them. We can call this the computational theory of mind. This term was coined by Jerry Fodor, and it's been defended by many people, both in philosophy and in the sciences, including notably Susan Schneider. According to the computational theory of mind, mental states are symbolic states of the computer. Mental representations are symbolic representations, and mental processes are computational processes. Okay, so what does that mean? According to the computational theory of mind, inference is symbolic manipulation. So according to CTM, what it is for Noah to believe that there are 6 birds on his arm is for there to be a symbol in his head that represents that there are 6 birds on his arm. When he infers that there are some birds on his arm from the fact that there are 6 birds on his arm, he's performing, or his brain is performing, a symbolic manipulation that takes you from the first sentence to the second sentence. So now I want to present what I take to be a serious and I think devastating problem for this kind of view, which is that according to the computational theory of mind, content is actually causally irrelevant. So if mental processes are computational processes, then they can be specified independently of environmental relationships. This follows directly from what a computer is. So a computer is a system whose operations are characterizable in terms of the formal properties of its inputs, its internal functions, and its outputs. So what do I mean by formal properties? A formal property is a physical property of a system or a functional abstraction. So we can think of the implementational level as the kind of physical level, and we can think of algorithms as functional abstractions from these physical properties. And computations are an even higher level of abstraction from these properties. Okay. So when you say that a process is computational, what you're saying is that you can implement it in your system without appeal to anything beyond the inputs and the outputs of the system. Let's see. So computational states and processes can have semantic properties that relate you to the world. But crucially, those properties don't make a difference to how the system works. That's part of what makes computers so powerful, is that you can specify how the computer works without appeal to the environment. But because of systematic relationships between the symbolic states and the world, you can get the system to do what you want it to do. So here's a way of understanding why content is irrelevant to how computational systems work. So here's a diagram from one of my favorite books. It's The Pattern on the Stone by David Hillis. And if you want an introduction to the sort of conceptual side of computers and how they work, I think it's a great non-technical introduction. So this is what's called an OR gate. It's hydraulic instead of electrical, just to show that the implementations of computational systems can differ. There can be different physical properties. So as water flows in, it depresses the spring, and so water can flow out one side, and as water flows in the bottom, the same thing happens and it depresses the other side. So that's why it's called an OR gate, because it outputs water just in case there's water flowing in the top or water flowing in the bottom. But it doesn't compute, this hydraulic OR gate doesn't compute the function OR essentially. If we assign, for example, P to when water, let's see, so if we assign P to when water is flowing through the top and Q to when water is flowing through the bottom, then the system can compute P or Q if we assign P or Q to water flowing out the end. However, if we assign P to water is not flowing through the top and Q to water is not flowing through the bottom, then the system computes AND. So water is not flowing through the end represents P and Q. So what logical operation the physical system performs depends on how we assign semantic contents to the physical properties of the system. As programmers, we make those choices. And so we get the system to do what we want. But importantly, the system causally works the same way, regardless of how you assign content, whether you assign content to water flowing or not. The system works exactly the same way. It's the water flowing that causes the system to behave as it does. Okay. I want to point out next that the computational theory of mind is a simplifying assumption. So if a system is computational, then you know how it works. You can specify how to build it without taking into account its relationships to the environment. So without taking into account what it represents. Francis Egan has a great paper talking about how useful this is in thinking about both computational processes in neuroscience, but also in cognitive science more generally. But for that very reason, what you're doing when you're saying that a system is computational is you're saying that the contents are not causally relevant. You're saying that you can specify how the system works independently of its worldly content. But I think for us, crucially, for beings that have minds, what you think matters. So I think that, for example, in contrast with computational systems, we have mounting evidence that content is causally relevant. So many scientific disciplines make essential appeal to mental contents. Social psychology, economics, linguistics, animal behavior theorizing. All of these fields make really essential appeal to semantic contents, and there's actually a history of trying to eliminate them with a high degree of failure. So it seems like we need to, when we causally characterize how animals and people do what they do, we have to appeal to semantic contents. Moreover, I think that one reason why a lot of work in AI to build genuinely intelligent systems has failed is precisely for this reason. We are systems that are genuinely semantic systems, and we've been trying to build purely symbolic systems that can behaviorally replicate us. And I don't think we can do that. And so that's why I think AI has reached a kind of stalling point in developing genuinely intelligent systems, not just systems that are really great at some specialized task, but systems that have the kind of capabilities that animals and humans have. So at this point, you might be asking a question, like, doesn't computational neuroscience already show us that we can replace semantic characterizations with neural or computational ones? Isn't that what you've been studying for probably years now? And I think not. I think that there's an important slip that often tends to happen. And I'll just provide one example of it. So I think that we have tons of evidence that neural manipulations can affect mental processes. But what we don't have is the good evidence for the claim that we can specify mental processes purely neurally or purely computationally, which is what this kind of simplifying assumption of the computational theory of mind would require. So I think we're a long way from showing, and we'll probably never show if I'm correct, how some kind of intracranial specifications can adequately characterize mental processes. And just as an example of how this kind of, I think, slip tends to happen in the literature, we have claims like, for example, John Bickel making this claim that current reductionistic neuroscience now provides causal mechanistic explanations of behaviors routinely taken to indicate cognitive or mental function. So in this paper, he's saying, look, we now have these reductionistic explanations. But then on the very next page, you have a kind of concession that what we really have is showing how underlying neural manipulations can affect mental processes. Not that we have some kind of replacement for the mental characterization in neural terms. And I'll let you read the slide. But I think this sort of slip happens all the time, and we should be really careful that we're not overblowing what current neuroscience can explain. So to return to, I think, what is kind of a key point is, I think, when we make semantic generalizations, when we're explaining what we do using the mental content, they're relational. They relate us to the world. So it's because Neva sees a pelican that she walks to the edge of the beach. So what she sees is something in the world. That's a relational characterization of her mental state, and that causes a certain world-involving behavior. And so what we want to understand is how you relate what happens in the brain or what computations are occurring in the brain to this kind of relational mental characterization. Okay. So these semantic generalizations cross-cut potential formal inputs and outputs. And here's just a toy example to get sort of what I mean here. So take the rule, if a colleague invites me to dinner, I don't show up empty-handed. Okay, this is a semantic rule that describes my behavior. Now, the invitation might come in any sort of form. It might come as an email. It might come in snail mail if somebody's being particularly fancy. It might be a verbal invitation. And the gift that you bring might be flowers, it might be wine, or it might be a toy for your friend's child. But there might not be any particular connection between what form the email comes in, what form the invitation comes in and the kind of gift that I bring. The only generalization you might be able to make is if a colleague invites me to dinner, I don't show up empty-handed. And moreover, you might have the same behavior as an input that's not an invitation. Say someone is practicing inviting somebody else to dinner and they want your sort of advice on how they're doing it. Or you might bring a toy along but not intend to give it as a gift, right? It might be in your bag and you might bring it. So this is an example of how the different potential, and if you can't distinguish these different distal inputs and outputs, good luck trying to get formal proximal inputs and outputs. So say retinal stimulation or motor outputs, right? So the point I want to make here is that the way we explain behavior, there's no hope of finding a unified formal algorithm for implementing these kinds of generalizations. The implementation is going to be very different depending on features of the context. So one thing you might think here is that, is she just being pessimistic about neuroscience? What are we going to do? And no, I just think that things need to get more complicated. So I want to briefly compare the biological process of thermoregulation. And this is just a diagram from an introductory textbook about thermoregulation. And what you'll see here is at the bottom, there are lots of different mechanisms for thermoregulation. And the organismic capacity for thermoregulation is a whole organism capacity that's robust across a range of contexts and environments. And the way that it's implemented in the organism's body is that you have different mechanisms that are active in different contexts, and they're related to each other in often very subtle ways, so that the whole organism has this robust capacity across contexts. So we're not expecting there to be one mechanism for thermoregulation. We're expecting that there will be different mechanisms that are coordinated in pretty subtle and sophisticated ways to get the robust organism level capacity. And so I think we should start thinking about mental capacities in this kind of way, where we should expect there to be multiple computations occurring. And part of the explanation is that we want to understand how these are subtly coordinated in specific contexts to generate the robust relational mental causal processes. Okay. So I want to say one thing about why we should expect mental generalizations to be at a different kind of scale, a more relational scale, and why we should expect there to be robust causal generalizations involving mental contents. So if you are just merely representing something that is, say, ecologically advantageous, the connection between the internal representation and the thing that it's representing is contingent. It's going to require a certain setup between the internal representation and the environment for that representation to be ecologically effective. But if you have a system that is genuinely causally related to the thing that's ecologically advantageous, that system is going to be more robust. So I think we should expect a kind of evolutionary selection for increasingly systems that can relate to the very things that are useful for them, as opposed to things that merely are causally driven by internal representations of those things. Okay. So I think it's going to be much more likely that mental capacities are these whole organism relational capacities than that they're just internal computational capacities. And so what that's going to mean from a computational perspective is that we have to look at how these mechanisms are sensitively coordinated with the body and the environment to implement these content-sensitive relational mental processes. Okay, so now what I'll do is I want to introduce the terminology and the conceptual framework I have for thinking about explaining how lower level processes give rise to higher level processes, and show how it relates to this kind of issue of semantic content. Okay, so just as there's causal structure in the world, I think there's what I call generative structure. So whereas causal relations are the ones we want to look for when we want to explain how things unfold through time, I think generative explanations are the ones we should look for when we want to understand how the world structures itself into more complex kinds, properties, and regularities. And I think we can apply the advances that we've been making in causal modeling over the last several decades to better understand generative structure. So yeah, I will go through this again just because I think it's important, even if you watched yesterday. If you didn't watch yesterday, this is particularly important for understanding how we can go from the more general things I've been talking about to more specific models. So when we're studying causation, one particularly useful way of understanding what we're doing is we're trying to represent or model what makes a causal difference to what. So instead of trying to specify general laws, what we're trying to do is we're trying to study certain asymmetrical relationships. So one of my favorite examples from philosophy is that The flagpole explains the length of the shadow and not the reverse, because it's the height of the flagpole that causes the shadow to be a certain length, and not the other way, even though they're equally predictive of one another. Causal models are often very context specific. So what causally explains the length of the shadow in one context might be different from what causally explains it in another context. You can use pretty sophisticated modeling tools, which I'm sure you have been and will continue to go into more depth into over this summer school. You can use these modeling tools to study causal relationships. And you can specify pretty complex structures. So one example from it's a real example, but it's a philosopher's idealization, is that taking birth control both decreases one's risk of thrombosis by preventing pregnancy, but it increases it by producing a certain chemical. So if you just looked at the relationship between taking birth control and thrombosis, you wouldn't see a relationship. But if you tease apart the subtle causal structure, you can start to see how there's actually rich relationships relating all three of these variables. Okay. So I think generative difference making is a different kind of structure. It's how the world structures itself into more complex kinds, properties, and regularities. But it should be understood analogously. So these explanations are asymmetric. So it's the brain that explains the mind and not the other way around. They're often context specific. So what explains a certain mental process in one context might not explain it in another, or how a decision is implemented in an AI or an octopus might be different from how it's implemented in a human. Work is in its early days here, but I think you can, there's some promising work that you can transfer a lot of the modeling tools and discovery algorithms from the causal context to the generative context. And really importantly for our purposes is that when we think about things in this way, we're thinking about specifying complex structure. So we're looking to explain robust systems level behavior, which means we're often going to be looking at how underlying mechanisms compensate to preserve the same higher level function. So just as in the birth control thrombosis case, you're not going to get, just looking at them, you might not see that a manipulation of birth control affects thrombosis. You might not see that a manipulation of a certain neural mechanism affects the higher level behavior, but that doesn't mean it's not relevant. Okay, and lastly, and this is important, just as with causal explanations, you don't define your explanandum in terms of your explanans. If we're thinking about explaining mental functions using neuroscience as generative explanations, we're not going to either start with or end up with definitions. We're going to leave these mental functions in their own relational terms and seek to understand how neural and computational processes make a generative difference to these mental functions. Okay, so because I'm running a little short on time, I'm going to, well, let me just say this one thing. So to draw things back together, it's okay if we think about, if what we're thinking about our project, if we're thinking about our project as generatively explaining mental functions in terms of neural or computational properties, it's okay that mental processes exist at this different relational scale. That's not a threat to neuroscientific or computational inquiry. It just means that our work is harder and we have to include the body and the environment in explaining these mental processes. Okay. So by drawing this all together, we should think about explaining, so the generative methodology that I've developed says that we need to use 3 distinct models and keep them separate in understanding how computation gives rise to mental functions. There's the agent model, which is the higher level thing we want to explain. There's the basis model, which is the neural or the computational specification. And then there's the generative model that explains how the lower level phenomena give rise to the higher level phenomena. Okay. So as an example of thinking about how this kind of generative approach works in another context, I'll end by discussing some work that I've been doing in collaboration with roboticists at Penn. So we've been looking at how you can use a kind of generative approach to empirically ask the question, what representations do you need to build robots that exploit certain affordances? Do you need to build robots that explicitly represent those affordances? Or is that the most efficient and effective way of building them? And so we have a recent paper, and here's just a table where we go through, we do a bunch of different case studies and show how you can separate out the question of what is the affordance that the robot is exploiting? What is the internal computation that's performed? And how does that internal computation in context get the robot to exploit the affordance? And so just to give an example, here we discussed a case of how you can get a robot to efficiently stand on uneven terrain. And it turns out that in that context, all you need are internal measurements of the draws on the different motors, and that is enough to allow you to compute the efficient standing position. So, of course, this isn't enough to get you a full, robust exploitation of affordance, but you can see how these different mechanisms, none of which explicitly represent the affordance or explicitly represent the environment, might be coordinated to get the robust relational overall behavior. So let's see. So the thought here is that although we're sort of in early days of this, perhaps we can go from building robots that whose behavior is based on sort of one or a couple of these mechanisms to building robots that genuinely exploit affordances by sensitively coordinating these different kinds of representational processes. And maybe none of them, it's an empirical question now, maybe none of them actually represents the external relational affordance. Maybe the representations you need are much more local and proximal and context specific. So in this paper, we discuss in some cases where the roboticists did use explicit representations, and in other cases they didn't. And what we are trying to do is motivate this as an empirical question, not as a sort of conceptual question that has to be answered before we do our research. Okay. So let me just summarize what I've done, and then I can't wait to hear from Pascal and Megan and the rest of you. The first take-home message is that we shouldn't assume mental processes are computational processes. That's actually a really serious assumption, and we have lots of reason to think that it might be false. Many mental processes are likely to be inherently content sensitive in a way that computational processes are not. And so there's going to be an important distinction between the two. So we shouldn't just assume that Marr's computational level is the mental level. We should keep them separate. What computations we need, moreover, is an empirical question. The relevant computations are, I think, likely to be much more local and context specific. And a lot of the explanation is going to go into how they're related to each other in context to give rise to the higher level, robust mental process. So we should keep these separate. We should model mental processes independently using agent models and seek to explain them in terms of generative models that show how compensating computational mechanisms in body and environment jointly generate the content involving process. Okay. And just before I end, I want to thank my research group, Mira, and my collaborators in Penn Engineering, and particularly Daniel Kodacek and his lab. Thank you.
Thank you, Lisa. That was awesome. We've got some great questions here. But first, before we go to the general Q&A, let's the whole point here is that now Pascal and you can have a conversation about this. So this is great. So do you want me to leave the slides up, or do you want me to take them down? What would you prefer?
Could you leave them up for now?
Yeah, let's
Just in
leave
case
them
we
up.
need them.
Let's leave them up. Okay. And so I'm going to do this now and make us a little bit bigger so that you guys can see each other a little better. So yeah, please go for it. I'm just here to facilitate.
All right. So Lisa, thank you so much for clarifying this. That was very interesting. I do agree with you that the field has been held back by playing fast and loose with the term of maybe the naive use of the term computation. The conundrum that I find myself in is in a way that I find that I agree with you too much. One of the first papers I wrote in grad school was exactly that the brain is not a computer, neurons are not computing. We need to be very careful about the use of those terms. And more broadly, I agree with you that the field has been held back, or I would even say marred, by misunderstanding Marr for 30 years. So I'm in a conundrum. So I would say I'm not going to challenge you on any of this, but I'm going to ask you to clarify on some things that I think would be helpful for everybody to clarify, because I actually agree with you. I almost on almost everything I agree with you. So one thing is, since my class paper almost 20 years ago, and if any computer scientists are here, maybe they can confirm this, isn't it literally true that the brain is a computer by the computer science definition? And here's the computer science definition. You take an input or a bunch of inputs, you feed them into a processor, you execute instructions on them to produce an output. So this input-output mapping, and I know this because I took a computer science class, is defined as computation in computer science. If any computer scientists are here, maybe confirm that in the chat or in the comments. But what do we say to that? That is by definition true, that the brain or the mind is a computer, because that's how computer science defines computation.
Okay, so thanks. I would say a couple of things. So one is the brain might be a computer, and it could still be true that the mind isn't a computer. So in order to so it could be true that neural processes can be specified in terms of their inputs and internal processes and outputs. Well, that's not true of mental processes. So mental processes might be this relational thing at a different scale, even if neural processes are computational. The second thing I want to say is that it's actually a really open question whether neural processes are always computational. So some of them are. We can isolate certain neural processes and describe them in computational terms. But I think we have often underestimated the way in which we are causally coupled to our environments and to the body and the environment in ways that make it really hard to put causal joints between the neural and the bodily or the environmental. So to describe a neural process as computational, what you're saying is that you can carve off the inputs and the outputs, and you can explain how the internal system works just in those terms. And it's not obvious that that's the most perspicuous way of describing these causal systems, which are often highly coupled. So, yeah, okay.
So as a follow-up question, and which also comes up here in the comments in the chat, which I also had, was if you, how do I say this? And I mean, yes, but if you go with that logic, then you would have to assert that there's something about the mind or mental processes, which someone actually asked us to define, that are not just reducible to what's going on in the brain, which is ion flux ultimately, and in an actual computer, electron flux, right? So what would you say that is that you cannot reduce to that?
So I think that the relationship between the brain and the body and the environment is really crucial here. So I'm a physicalist. I think that the physical facts give rise to the rest of the facts. But I do think that the mind is not just reducible to the brain. I think it's only reducible to the brain in body, in environment. And that's the only way we're going to understand the way in which mental processes are these genuinely relational things where we genuinely interact with the environment.
But what I'm saying is, or what people in the chat's also saying is, but fine. So it's not just the mind is not just representing what's going on in the brain, but also in its immediate environment and the body, but also physically, right? I mean, it's also physics, no? I mean, just forces and energy, basically, no?
Yeah, so there are all these really interesting problems that arise for any physicalist view, how the mind or mental processes are genuinely causally efficacious. If everything is determined by the fundamental physics, how could what we think matter?
Right.
How could it make a causal difference? And that's going to be a problem whether you think that the mind is reducible to the brain or whether you think it obtains in virtue of a brain-body environment. That there's going to be the same issue there. I tend to think that, and this is sort of work that's coming up. I haven't published on this yet, but I tend to think that once you separate out causal explanation from generative explanation, you can think that everything generatively depends ultimately on the physical level, but that certain causal, when things structure themselves into new kinds with new properties, they can actually make a distinct causal contribution on the world. So we don't, and we probably can't, and don't have to think of the underlying physical explanation as being the full causal explanation of the world.
So I don't want to hog this too much and go to the comments soon, but I have 2 or 3 more comments just following up on what you said. So I think you're right. I think it's critical to go to the difference between generative versus causal to understand this. But I have a follow-up on what you just said. Isn't the implication what you said that the brain is special, that it's not just physical? And in your conception, where does semantics come from then, if it doesn't come from the physics? Or maybe I misunderstood that.
Okay. So I don't think the brain is necessarily special. I think that in the sense that only the brain could give rise to the mind. Well, I think that the mind is just a different higher level kind. So just as you can have organization into organisms that are alive, that reproduce, that have all sorts of properties that other kinds of physical systems don't have. Some of those organismic systems have minds, and those are just different properties at a higher level. I don't think that they're any less natural than other kinds of systems in the world, but they are different, and it's important to understand the ways in which they're different.
What about a wider conceptualization of computation? So, for instance, Hopfield, as you probably know, conceptualized even the weather or the cosmos to be computational, it's computing something, because he has a more expansive view of what computation is, so a nonlinear mapping from inputs to outputs. Douglas Adams has the same concept about the planet Earth is a computer, basically. So what do you think about that? What would you say about that?
Yeah, I think there are 2 things to say. So one is part of what's at issue when we're thinking about the mind as a computer is, and not everybody has this assumption, but it's the predominant assumption, is what we can call intracranialism. So the idea that it's what's in the head, that's the computations that are that give rise to the mind. And that's mostly what I'm focused on rejecting here, because that's kind of the main assumption of computational neuroscience. So you could have a more expansive view of, so one way you could respond to what I've been saying is that, well, mental events are computational under some description, but it's just going to be a wider, more relational kind of computation. But even that I don't think is quite right, because, let me say that that would be an important, sorry, I'm seeing some popping up on, are we okay with the technology? Is everything going okay? Yeah, Megan's nodding. Okay, so we're okay.
Sorry, yes.
Okay, so that's the first point, is that computational neuroscience would have to change pretty substantially, even if they were going to maintain that mental events are computational events and mental kinds are computational kinds. The second point is that if you have this wide, expansive view of computation, it's not clear in what sense it's explanatory. In what sense is that hypothesis a different hypothesis from other hypotheses about the mind? And so I think if we moved in that direction, I would want some, I think we're often at risk when we use computational terminology in cognitive science, we're at risk of thinking that we understand more than we understand.
I mean, I want to end with that because I don't want to, like I said, take all the time. But I do have a follow-up on that. I mean, don't most people think that their mind is tied to their brain because A, you don't feel my pain, and B, if something changes in my brain, say you take a drug, that changes your mental state. Isn't that why most people think that their brain is tied up to their mind? Does it make sense?
Yes.
Not
and,
just moral.
Well, so I completely agree that your mental states are largely dependent on your brain, and my mental states are largely dependent on my brain. The question is whether you can isolate my decision-making process inside of my head. And that I want to deny, but I don't want to deny that my brain is really important for explaining my mind, and your brain is really important for explaining yours.
So let me press you on that, because you seem to channel your inner Gibson, so I'm going to channel my inner Ned Block. What he would say, I think, at least if he still believes what he read in his paper, that let's take area MT, which has been linked to motion processing. What he would say, or what he did say in his paper, is if you lesion MT, you can no longer perceive motion consciously, if you believe what we know from primate experiments. And so you would argue that that's causally necessary. Conversely, if you stimulate area MT, primates report motion perceptions in direction. So you can show that it's causally sufficient. So what else is missing in here?
Yeah, good. Okay, so this was the slide that what's relevant here is
and maybe
the
I
slide
misunderstood that.
discussing the example from John Bickel's work. But I think that to show that, so there are lots of experimental studies that show that you can manipulate neural features and use that to manipulate mental features. So that shows that neural processes are what I call generatively relevant to mental processes.
Yes.
Mental processes partially obtain in virtue of neural processes. But I think that, so they can be necessary. There's no, I completely endorse the claim that neural processes are necessary for mental processes, at least in biological organisms. The sufficiency claim, however, I think is much more difficult to establish, and that's where we start to get into trouble. So you might be able to manipulate a neural feature and manipulate a neural feature and change a mental feature, but that's only against the context of the rest of the brain and the body and the environment. And so establishing sufficiency of neural processes for mental processes is a much more difficult thing that, quite frankly, I think we haven't done.
Right.
Nobody's done it. Yeah.
Just to clarify, to push this to the extreme, so you would say a brain in a dish, or an area MT in a dish, or an area MT neuron in a dish would not necessarily perceive motion, even if you stimulate it the way you do it in a real brain.
Exactly. Yeah.
I see. And so, last point, and then I will open it up because I know there's more questions. But isn't this just playing fast and loose with the definition of what causality is? I mean, even Aristotle would agree there's multiple, there's a chain of causality, right? So why did he die? His heart stopped, which we could put on every death certificate. Eventually, your heart stops if you die, right? Whereas you could ask, okay, why did your heart stop? Maybe he was sick or someone shot him, right? I mean, where does the, maybe I'm misunderstanding, where does the generative process do better than that? Does it make sense?
Good. Yeah. So we got into this in a little more detail yesterday.
I missed that. I'm sorry.
No. Of course. But I think that generative structure is different, but analogous to causal structure. So I used the example yesterday of a cake. So you might have two different classes. So Megan's like, yeah,
this is like my favorite way of explaining this. Yeah.
Okay, good.
Cake is a lie, right? Go ahead.
So you have a cake on the kitchen counter, and you want to ask, why is there a cake there? And there are two different kinds of questions you might ask. Someone might have, it might be someone's birthday, and so somebody mixed together the ingredients and put it in the oven and took it out and then set it on the counter. And that's a causal explanation for why there's a cake there.
Mm-hmm.
A generative explanation for why there's a cake there appeals to the molecules, the sugars and the carbohydrates that constitute the cake. And you might want both kinds of explanations, but they're different and they're non-competing. So one explains how things evolve through time to get you to the point in time where there's a cake on the counter. The second kind of explanation explains how simpler kinds of things are structured into more complex things. In this case, sugars and carbohydrates and so on to get you a cake.
Question for you on that note. So wouldn't wouldn't Marr's level of implementation be the molecules and all that, which is the generative level, you would say? Wouldn't it be the computational part, making the cake, executing the recipe, be the Marr's algorithm part? But isn't there like a third level, the strategic level? Why is there a cake? Because it's someone's birthday and you want to feed your guests, right? No.
Yeah. So Marr famously said, he gave two different descriptions of the computational level. He said what computations the system computes, and then he said what the system is up to and why.
Right.
Right, and these are the same as long as what the system is up to is computing. But what the system is up to might be a more relational, world-involving thing, in which case, in order to have a full explanation, you might not just need a computational description. You might also need this relational description.
But you also need telos, right? You bake the cake because it's someone's birthday and you want to feed your guests. It's telos. I know it's a dirty word in science, but you have to. The cake didn't just randomly appear out of quantum fluctuations, right?
Right, but I think one thing you can, so the telos question is, I think, a really interesting question, and we can maybe we can use a different example of causal processes that don't involve human agents as to clarify the distinction. So you might ask, why is there a tree trunk across the trail? Well, there were heavy winds yesterday that blew the tree down. That would be a causal explanation. A generative explanation would look at how the molecules and so on were organized in that location of space to give you a tree trunk.
Right. Okay. I'll leave it at that. But I like I said, could you leave it with the following thing? Marr was wrong about what the computational level is. It's more like the strategic level. His algorithmic level is the computational level, and the implementation level is the generative level. Is that fair?
Well, I think we need at least four levels in explaining the mind. So I like Marr's computational, algorithmic, implementational distinctions. Okay. I think that those are all important because you have different, you can decide on the computation that needs to be performed, and there still be a question about what algorithms you need to
exactly
to execute it.
So why don't we go to the comments, because there's a lot of good comments.
Yeah. Great. I was about to cut you guys off because we technically only have 5 more minutes. And so, but fortunately, we also have nobody right after us. So if we want to run over by a little tiny bit and people want to stay, then we can do that too. But we do have some good questions.
Great questions.
The top voted question actually is from Gunnar, who is another, organizer at NMA. And so the top question is, how is mental content different from the concept of cognitive set or internal state, with a follow-up of internal state would reflect brain processes, including memory, the body's state, and the environment. And if you guys want to read, you can click on the ask a question box and you can see those as well.
Oh.
Let's see. I think mine's, let's see, view chat. Is there a way to organize it where it's not, so I think mine is just the real-time feed.
Okay. The ask a question button at the bottom will show you.
To the left of that, yeah.
Okay. So the question is about mental content versus cognitive set or internal state, and the distinction there.
So, okay. So I think that, so I think it's, subtle. Sometimes, so internal states can reflect the body's state in the environment causally, in that the body and the environment can affect your internal state. But when we explain how people do what they do, it's an open question. And I think part of what I was arguing is that it's not productive to think about our behavior as just being driven by these internal states that represent the world. Rather, when we say Neva walked to the end of the beach because she saw a pelican, we're giving a relational characterization. We're saying how she's related to the world perceptually, and that might not, and how that affects her behavior. And it might not be a unitary internal state that is the cause of that behavior. So the distinction that I'm trying to draw is I'm trying to say we have this relational characterization, this perceptual, cognitive, action, relational characterization, and it's a substantive empirical assumption to then say that each of those components relates to an internal state, and you can causally characterize what happens mentally in terms of this intracranial process. That's a substantial empirical assumption that we don't need to hold to do computational neuroscience.
Okay. Great. Sounds like, Pascal, you don't have a follow-up there, which gives us time for, well,
I was going to say, I think we should go to the comments.
Yeah, it gives us time for more stuff. So the second most upvoted question is from Amireza, who asks, we capture some characteristics of the brain with our computational tools. Still, we can't capture semantics using these tools. Mm-hmm. Do you think we have a shot at understanding and modeling this semantic content? If we do, which way should we start looking? Can we somehow model non-computational semantic content using non-computational tools, if such a thing even exists?
Great. Okay, so this is where, and I encourage you, if you're curious about this, I encourage you to watch the video from yesterday, because we get into a little bit more depth about thinking about the generative methodology. But I think that the thing that's really important is to distinguish your what I call your basis model from your agent model. So the basis model is going to give you neural and computational descriptions and non-mental descriptions of the body and the environment. And the agent model is going to give you a description of the genuinely semantic processes. Now, you can use formal tools to represent those, to represent what the agent is doing and how, and I think that's great. Like using causal Bayes nets to represent how agents make decisions, I think is great, and we should do it. But what we shouldn't do is we shouldn't assume that because we have a formal model of how the agent makes decisions, that we can just straightforwardly implement that model inside of the brain and have an agent that works the same way. So one thing that a lot of philosophers who work in this area bring up is that you can, just because you're representing how the agent does what they do computationally, doesn't mean that you the representation is a replication of how the agent is doing what they're doing. So yes, we can still study genuine semantic content and genuinely semantic decision-making, but we should keep separate our representation, our formal representation of what the agent is doing from our computational representation of the brain.
Pascal, do you have anything that you want to add to that?
Oh no, I'm just responding to so many comments. I think I said enough. Go ahead.
Okay. Yeah, I think I don't have anything to add there. I think this is a really important question, though, which is, and this is exactly the type of question that we as computational neuroscientists also should be asking, which is, with the tools that we have, can we ask the questions that we really want to be asking? And are the answers that we're going to get the ones that we think do we understand the answers in the way that they're actually like true, in the sense that you've discovered this representation that you think is related or you've extracted from the brain, but if that is actually the representation that the brain is using, or that is actually like present in the brain versus one that is just computationally tractable for us, given the tools that we have right now, it's a really hard question to answer, but it's a really important question for us to think about, for sure.
I mean, maybe one thing.
Yeah.
So would you say semantics emerges as from the interaction? I mean, one thing that's still been left in the air is So where does semantics come from then? And it's probably, if I understand you correctly, you would say from the interaction between the brain and the environment, right?
Mm-hmm. Yeah. And so emergence is a term that and I saw it pop up a couple of times in the chat. It's a term that I avoided in my talk just because it means so many different things to different people.
Right.
So one thing I want to avoid is this idea that the mental kinds can't be explained in terms of more fundamental kinds. I think they can. So some people, when they talk about emergence, they think it's somehow this inexplicable arising out of physical processes, and I don't think that's true. I think we can explain it. But yes, I think that mental content and content involving processes emerge from the complex interaction of the brain, body, and environment. And our task is to understand how that happens.
Cool.
Great.
Okay, so we're a little over time here, but maybe there's one more that we can kind of end on, because I think it's kind of forward thinking. So, hang on, there was this one. I lost it. Hang on. Well, okay, we'll do the top voted one then, because I lost the one that I was thinking of. So there's one more here from Wenjuan, who is asking, and I hope I pronounced that right. I think many neuroscientists acknowledge that the reductionist assumption in neuroscience, but the limitations of neuroimaging techniques and the premises of scientific methods make it hard to study at the whole organism or environmental level, as you're kind of suggesting we need to do. Are there any imaginations of new ways of doing neuroscience that will incorporate this inactivist perspective? And actually, this is a good place to stop, because you're pushing for us to study the mind and the brain outside of just the mind and the brain. So how should we do that?
Yeah, I thank you for the question. And I think what I want to emphasize is that this work is really difficult, and I have a ton of respect for neuroscientists who are on the ground and doing this really difficult work. I think that what I am urging we do is, and to some extent it's difficult given the sort of academic structures and incentives that are set up for us, but I'm asking that we really think about separating out our modeling of the mind from our modeling of the brain. And I think that's the first step. And that's that's a tractable thing to start doing. And then to really use the kinds of modeling tools that we have to investigate how features of the brain give rise to features of the mind. And I think that's a first step. I agree that this is really difficult, but I also think that we shouldn't just look for our keys underneath the lamppost, because that's where it's easiest to see. We should try and take our flashlight with us and go around and try and look for the answers where we think we're most likely to find them. But I think progress is going to be incremental, and I hope that maybe some of you are inspired to start thinking about things in terms that challenge the kinds of assumptions that that you might have learned. Yes.
So to echo that, I think as a field, to be somewhat self-critical, we've just been better at building better and better lampposts, and that is actually one of the reasons I now focus on behavior, because that is, how do I put this, closing the loop with the environment. So you're putting something back out in the environment that changes your environment as like a cybernetic system. So I think. Yeah, I echo that also. There's lots of reason to be hopeful, even though we're not there yet.
Yeah. Well, this is a fantastic place to end. I know we have actually so many more questions that we didn't just get to, but I think that if we wanted to get all of them, we would be here for hours. But thank you for your great questions. Take them offline. We can continue the conversation via all sorts of asynchronous methods. This was a really, really fun conversation. Thank you again, Lisa, for being here and sharing this with us. Thank you, Pascal, for being here and keeping the conversation going and asking so many fantastic questions. This was really informative and fantastic for me to watch too, to just kind of sit here in the background and just listen and absorb. So thank you both for excellent discussion. And And thanks all to the audience for being here too. And I hope you've kind of had your mind expanded a bit in terms of thinking about what these models are buying us that we're learning about through Neuromatch Academy. So thanks again. And we'll see you next time. Actually, part of words of wisdom. Anything?
No, just thank you, Pascal. Thank you, Megan. Thank you, everybody. It's really thoughtful scientists like you all that are going to bring us to the next big wave of understanding. So I'm really inspired by both of these sessions and just how thoughtful and amazing you all are. So thank you.
Even the fact that we have 2 sessions on this actually is a good sign.
Right.
Yeah, exactly.
Yeah.
Okay. Great.
Thank you
well,
all.
Thanks very much, and we'll see you guys next time.
Mm-hmm. Yes.
Okay.